Assalamualaikum warahmatullahi wabarakatuh, and a very good day to Doctor and my fellow friends. Today, our group will talk about nanotechnology in energy and electricity. First, we will talk about history of nanotechnology. American physicist and Nobel Prize laureate Richard Feynman introduced the concept of nanotechnology in 1959. He described a vision of using machines to construct smaller machines and down to the molecular level. After 15 years, Norio Taniguchi, a Japanese scientist, was the first to use and define the term nanotechnology in 1974. As we can see here, this is the timeline of the history of nanotechnology. In 1959, Richard Feynman gave a talk on nanotechnology. In 1960, William McLellan constructed the first 250 microgram model. In 1974, Norio Taniguchi coined the term nanotechnology. In 1985, researchers at Rice University discovered fullerenes, or more commonly known as buckyballs. In 1986, Eric Drexler made the concept popular with his book Engines of Creation. In 1991, Sumio Iijima discovered the carbon nanotube. In 1997, Zybex is founded and is the first company to research nanotechnology. In 2006, Naomi Halas and Jennifer West are leading the field in nanoparticles combating cancer. And lastly, in 2005, Gunther Oberdoster coined the term nanotoxicology.
So now let's move on to the nanotechnology concept in energy. Nanotechnology is revolutionizing the energy sector by enabling more efficient and sustainable technology for generating, storing, and distributing energy. So the first one is nanomaterials such as graphene, carbon nanotubes, and silicon-based semiconductors are enhancing solar cell, batteries, fuel cell, and thermoelectric devices for higher performance. They improve efficiency, energy density, charge or discharge rate, and durability. Carbon nanotubes are investigated for low-resistant electricity, which allow its transmission to cut the grid loose. Nanosensors are enabling real-time monitoring for power grids and nuclear reactor. And then the next one is a nanostructure catalyst, and membranes are enabling more efficient hydrogen production via water electrolysis and reducing the cost of fuel cell. Nanomaterial can also capture and convert CO2 into fuel and chemical. And then, the nanoparticles are being used to optimize combustion process in power plants and vehicles, reducing fuel consumption and emission. Nanocoatings are enhancing the efficiency and lifespan of gas turbines. And then, the next one is a nanotechnology, also enabling new energy harvesting approach like piezoelectric nanofiber woven into clothing to generate electricity from motion, and thermoelectric nanostructure to convert waste heat into power. Did you know that? Now, let's move on to the nanotechnology concept in electricity. Nanomaterials like carbon nanotubes are being explored for ultra-low resistant electricity transmission wire to reduce the grid loss. This could significantly improve the efficiency of electricity distribution networks. And then, the nanosensors are enabling real-time monitoring of power grids, allowing for dynamic load and error management. This is crucial for integrating more decentralized renewable energy sources into the grid. The next is the nanostructure materials are being used to develop more efficient and durable components for electricity generation, such as the first one is the nanoparticle and coating to enhance the efficiency of gas turbine and other power plant equipment. The second one is the nanomaterial for more efficient and cost-effective nuclear reactor and separate nuclear waste storage. And lastly, the nanostructure catalyst and membrane for improved hydrogen production via water electrolysis.
So next, I want to explain examples about nanomaterial in energy and electricity with their applications. First, for energy, nanomaterials in solar cells. Their application is to improving the efficiency of photovoltaic cells. So there are three of nanomaterial. First, quantum dots. Second is graphene and titanium dioxide. So for quantum dots, these semiconductor nanocrystals can be tuned to absorb different wavelengths of light, enhancing the spectrum of light that solar cells can capture and convert it into electricity. And next, for graphene, this single layer of carbon atoms offers excellent electrical conductivity and mechanical strength. When used in solar cells, it enhances the transport of electrons, increasing overall efficiency. So last, we have titanium dioxide nanoparticle. Titanium dioxide nanoparticles are used in dye-sensitized solar cells to increase surface area for light absorption and improve electron transfer. It also leading to higher efficiency. Next, we have nano coatings on wind turbine blades. The application is enhancing durability and performance of wind turbines. So we have 3 nanomaterials in these nano coatings for wind turbine blades. First, erosion resistance. Nano coatings can protect turbine blades from the abrasive effects of rain, sand, and other particles, significantly extending their lifespan. Second, we have isophobic coatings. Nanotechnology-based isophobic coatings prevent ice formation on blades, which is crucial for maintaining efficiency and preventing mechanical failures in cold climates. Plus, self-cleaning coatings. Hydrophobic nanocoatings keep the blades clean by repelling water and dirt, ensuring optimal aerodynamic performance. So last, for energy, we have nanofluids for heat transfer in energy systems. The application is to enhancing heat transfer efficiency in cooling system. We have 3 nanomaterials in these types of nanofluids. We have increased thermal conductivity. Nanoparticles such as copper oxide and aluminum oxide enhance the thermal conductivity of base fluids. It also leading to better heat transfer rates. Second, we have stability and compatibility. Nanofluids are designed to be stable and compatible with existing cooling system. It also providing a seamless integration with minimal modifications required. Plus, applications in solar thermal system. Nanofluids are used in solar collectors to absorb the transfer more efficiently, improving the overall performance and solar thermal power plants. We have nanofluids for heat transfer in energy systems. The application is to enhancing heat transfer efficiency in cooling system. We have 3 nanomaterials in these types of nanofluids. We have increased thermal conductivity. Nanoparticles such as copper oxide and aluminum oxide enhance the thermal conductivity of base fluids. It also leading to better heat transfer rates. Second, we have stability and compatibility. Nanofluids are designed to be stable and compatible with existing cooling system. It also providing a seamless integration with minimal modifications required. Plus, applications in solar thermal system. Nanofluids are used in solar collectors to absorb the transfer solar energy more efficiently, improving the overall performance and solar thermal power plants. Last, for electricity, we have nanoscale energy storage materials. The application is to improving the performance of batteries and supercapacitors. So we have 3 nanomaterials in this nanoscale. First, we have lithium-ion batteries. Nanostructures materials like silicon nanowires and graphene are used to improve the anodes and cathodes for lithium-ion batteries. Silicon nanowires can store more lithium ions, significantly increasing the battery's capacity, while graphene enhance electrical conductivity and mechanical stability. Second, we have supercapacitors. Nanomaterials such as carbon nanotubes and graphene oxide are used in supercapacitors to improve energy density and power delivery. This material offer high surface area and excellent electrical conductivity, which are crucial for efficient energy storage and rapid charge-discharge cycles. Last, solid-state batteries. Nanotechnology enables the development of solid-state electrolytes, which are more safer and stable than traditional liquid electrolytes. Nanostructured solid electrolytes enhance ionic conductivity and enable the use of high-capacity electrode materials.
Alright, next is properties of nanomaterials in nanotechnology concept in energy and electricity. When nanoscale materials are decomposed, distinct changes in their properties can be seen. Quantum size effects lead to changes in the electronic properties of materials as they move from the molecular level to the nanoscale level. Physical and chemical properties of nanomaterials including size, shape, chemical composition, crystal structure, stability, surface area, surface energy, and other properties. Mechanical, thermal, and catalytic properties of materials can change as the surface area to volume ratio increases at the nanoscale. At nanoscale sizes, many insulator materials begin to behave like conductors. The surfaces of nanomaterials become reactive with each other and with other systems as the surface to volume ratio increases. As we can see here in this table, properties catalytic, increase in surface activity of particles; electrical, increase in electrical conductivity of ceramic materials and magnetic nanocomposites; increase in electrical resistance in metals; magnetic, change the point of magnetic phase transition, increase of coercivity and appearance of supermagnetism; mechanical, improvement in firmness and hardness of metals and alloys, and appearance of superelasticity; and lastly, optical, shift in optical absorption and change in fluorescent properties, and increase in quantum efficiency of semiconducting crystals.
Assalamualaikum, my name is Mame Sarah. Now I will explain about advantage, disadvantage, and impact of energy and electricity. First, I will explain the advantage. The first point is enhanced energy storage. Nanomaterial can significantly increase battery capacity and charging speed, as believed by silicon nanoparticle in lithium-ion battery. Supercapacitor using nanotechnology have a higher storage capacity and faster charging time. Next is efficient energy conversion. Nanotechnology can improve the efficiency of photovoltaic cell, touch material such as cotton dot and nanowires. In addition, nanostructure so thermoelectric material more effectively convert heat into electricity. Third, reduce energy consumption. Nanotechnology can improve the efficiency of LED lighting and create nanolayer for better thermal insulation, reducing energy consumption for heating and cooling. And the last is durability and cost effectiveness. Nanomaterial can stretch the energy infrastructure, reduce maintenance costs, and increase life expectancy. Over time, they can reduce the cost of energy production and storage by increasing efficiency. For the advantage, the first point is health and environmental risk. The health effects of nanomaterial are not fully understood, with potential toxicity posing risk during manufacture, use, and disposal. Accidental release into the environment can cause dangerous pollution. The next is economy and social concerns. The high initial cost of developing and deploying nanotechnology requires significant investment. Automation and new technology can replace jobs in the traditional energy sector, causing economic disruption. Besides that is technical challenge. Improving the production of nanomaterial can be challenging and expensive, and integrating nanotechnology with existing energy system may require substantial modification. And the last is regulator and security issue. The rapid development of nanotechnology often goes beyond the regulatory framework, which lead to gaps in safety and environmental regulation. The long-term effects on health and the environment are still unknown. The last is impact of energy and electricity. The first is environmental impact. Electricity power industry, business, and home, driving economy, growth, and productivity. Next is global impact. Access to electricity is unfairly distributed globally, with many regions lacking reliable access. And the last is culture effect. Reliable electricity access influences culture, practice, and lifestyle, enable entertainment.